This series focuses on data structures and algorithms content, and in this recording in particular I will talk the third part 3 of the insertion short algorithm subseries, complexity analysis, particularly big O analysis. We can see the complexity of an algorithm from the perspective of the amount of time required and the amount of memory space required, called as time complexity and space complexity respectively. Talking about the space complexity for insertion sort algorithm, this is the code for insertion sort algorithm. We can see this. You can see that the algorithm requires a small amount of function local memory space. For example, for the variables, correct position for peak, and exit, and also iteration indices variables I and j. And there could be some temporary memory space required when evaluating the functions. So this is the extra memory space required by the algorithm, and it is required for those variables I mentioned. This space does not grow with the data size, that means size of the array that is received. It remains the same regardless of the size, so or the length of the array received by the function. Therefore, the space complexity of selection sort algorithm is big O1. It is a constant space complexity. Now let us look at time complexity from top level or a course level. The course level analysis is not concerned with the detailed or precise counts of the operations involved. Here the external loop or outer loop controls or executes in sequence the entire logic of each pass of the algorithm. This is the logic that is executed in first pass and second pass, third pass. In the first pass, this code gets executed with I equals to 1. In the second pass, it is executed with I equals to 2, and this continues until this is executed with I equals to size minus 1. So there are total size minus 1 passes in this algorithm. In each pass, the algorithm sees the input as two sub arrays, the sorted sub array and unsorted sub array. The first element of the data array with index 0 is placed in sorted sub array. Second, third, fourth up to last elements are actually in unsorted sub array. That is the reason why iteration index I starts with value 1, the index for second element. The first element in the unsorted array sub array, which is the element with index I, is chosen as a peak value for each pass or for each external iteration. And correct position for peak is set to 0 to ensure that the default insert position will be the first element of entire array. In case if the inner for loop, the for loop which is inside, fails to update its value, the value of correct position for peak variable. That happens if the peak value happens to be the smallest value in the entire array. In the inner for loop, the if statement and assignment statement together is the thing that we consider as a dominant computational unit for time complexity analysis. There are total size minus 1 passes in this algorithm because the external loop iterates for size minus 1 number of times. Now if we look at this code block of the inner for loop, which contains the if statement and assignment for shifting the elements, it is actually executed for I number of times. In the worst case, if the exit flag causes to exit early, in the non worst case situation, the number of executions will be smaller. To repeat it again, it gets executed for I number of times for each pass in the worst case situation, but in non-worst case situation, the exit flag may cause the control to exit this loop early. Before that, that would be non-worst case situation. But we are sticking to the worst case situation, and in the first pass with I equals to 1, the code block is executed for one time. In the second pass with I equals to 2, the code block is executed for 2 times. In the third pass with I equals to 3, the code block is executed for 3 times. And in the last or final pass with I equals to size minus 1, the code block is executed for size minus 1 times. Now replacing the size by lowercase n, because size determines the length of the array. So when we put this in the formula, it is more convenient to use this n, the variable n. So we replace the size by lowercase n, and we can obtain the summation of this all this number of times this code block is executed, 1 plus 2 plus 3 plus up to size minus 1 in this form as expression n square by 2 minus n by 2. So this is because we have this expression, the dominating term here is n square by 2. Therefore, the time complexity is big O n square, and this is the worst case complexity, where we have assumed that both the outer and inner loops complete their maximum possible iterations, thus executing the code block of the inner for loop for maximum possible number of times. This happens when the function is called by passing an array whose elements are reverse sorted. If you want to sort the elements in the ascending order, but we pass an array where the elements are sorted in descending order. In average case scenario, we have when the passed array or the array received by the function has approximately 50% of the element pairs sorted in desired order and 50% sorted in reverse order. In that case, the inner loop will execute for roughly half of the possible maximum number of times iterations. By keeping in account the 50% of the inner loop iterations, we can get an expression which still have n square term as a dominating term. Therefore, the average case complexity is still big O n square. In the best case scenario, when the received array has all the elements sorted in the desired order, in this case ascending order, the inner loop will execute for only one iteration, and after the first iteration the control will just exit the loop. Therefore, you can assume that the inner for loop code block gets executed only one time in each pass, which leads to big O n complexity. This is the end of this recording. Thank you for watching this video.